The common ion effect is a tool we'll use to help understand what exactly is happening in a buffer. And I'm going to let you know right now that the common ion effect is basically a special form of good old Le Chatelier's principle. So notice how Le Chatelier's principle keeps following us around in Chem 223, and that'll continue on several more chapters too. But anyway, I digress. Here's the question. What is the effect on the pH of adding ammonium chloride to 0.25 molar ammonia? All right. Now, the ammonia equilibrium is right here. And like all weak bases, and ammonia is a weak base, ammonia reacts with water. It makes ammonium, the conjugate acid, and hydroxide. Ammonia is a base, so it creates hydroxide. All right. If we add ammonium chloride, all right, it's the ammonium part we're interested in. The chloride is the conjugate of a strong acid, HCl, and chloride was one of the ions that doesn't affect pH, but ammonium certainly does. If ammonia is a weak base, then ammonium is a weak acid. You can look up on the table of acids and bases and see that ammonium has a Ka. So if we add ammonium to this ammonia equilibrium, we're adding an ion, ammonium, which is common to the equilibrium, all right? And all it's saying is basically what's going to happen by Le Chatelier's principle, by the way, if you add ammonium. So what we'll do is we'll think about what happens when you have just ammonia, and then we'll think about what happens when you're adding ammonium to the ammonia reaction. Now, let's think about Le Chatelier's. If you start adding ammonium to this reaction with ammonia, ammonium is a product. We would expect the product to shift the reaction to the opposite side, to the reactant side. And in the meantime, hydroxide, which is also a product, will go down. Now, hydroxide is a pH thing, is a thing that affects pH. And if hydroxide goes down, that means you're going to end up with more hydronium. As more hydronium is formed, your pH should start shifting down. So, Le Chatelier says that the equilibrium should shift to the left. You're adding ammonium. Ammonium is a product. Products are going to move to the reactant side. The reaction will shift to the left. If it shifts to the left, your hydroxide concentration goes down. And because hydroxide times hydronium is always equal to that magical Kw, if hydroxide goes down, that means hydronium goes up. And if hydronium goes up, pH is going to go down. Now, that was kind of convoluted and might be a little weird, but here's another way to think about it. Ammonium is an acid, and if you add an acid to a solution, it'll become more acidic, so pH should go down just because you're adding an acid, and that's another cool way to think about this problem. So, ammonia by itself has some random pH. You start adding ammonium, an acid, and the pH should become more acidic. It'll go down. That's kind of the punchline here of what's going down. The common ion is just basically saying, all right, we're adding an ion common to an equilibrium, and what will be the effect of adding that ion? And in this case, because we're adding ammonium, it shifts to the left, hydroxide goes down, pH goes down as well. Kind of crazy. So there's multiple ways to think about common ion effect, and you just find the way that works best for you. Sodium acetate is added to an acetic acid solution. The pH of the solution will do what? Okay. Well, here's the punchline. You already have an acetic acid solution, all right? And that's fine. It has some pH. But you don't really care about that in this problem. You want to focus on what you're adding to the reaction. You're adding sodium acetate, okay? Well, acetate is the conjugate to acetic acid. And since acetic acid is an acid, automatically you know that acetate is a weak base. And that's what you need here. You're adding a base to the solution. And anytime you add a base, your pH should go up. So notice that I could care less about what you're adding it to. You're adding it to HCl, you're adding it to a blah, 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 you're adding it to an unobtainium solution. I watched the Avatar movie the other day and they were trying to get unobtainium as a chemist. It was freaking me out. All right, Prophet, back on. But anyway, you're adding here an acetate. Acetate is a base. So if you add a base, your pH is going to go up. And that's all it is to it. That's literally all there is. All right, ignore what's already there. You add a base, your pH should go up. You add an acid, like on the ammonium earlier, your pH should go down. Back to this problem. Let's find the pH of the 0.25 molar ammonia first. All right, this is before we add any ammonium chloride. And this is a cool review from the stuff from the previous chapter. No problem. So we'll set up the ice table. We're going to keep water out because liquids and solids are always removed. Initially, we have 0.25 molar ammonia, and we don't have any ammonium or hydroxide. So ammonium and hydroxide will increase by X. Ammonia will decrease by X. So at equilibrium, 0.25 minus X for ammonia, and ammonium and hydroxide are both equal to X. You can look up the Kb for ammonia in the table of acids and bases. If you do that, the Kb is 1.8 times 10 to the minus 5. And so 1.8 times 10 to the minus 5 equals ammonium times hydroxide divided by ammonia. Ammonium and hydroxide were both X, so that's X squared. Ammonia 0.25 minus X. And this is one of those places where you can absolutely get out your TI calculator or get out the solve function on your calculator and solve this. This would be a quadratic, etc., etc. However, if you remember from last time, if 100 times K is less than C, you can ignore that little minus X. And 100 times K, 100 times 1.8 times 10 to the minus 5 would be 1.8 times 10 to the minus 3. And 0.25 would be 2.5 times 10 to the minus 1. That's a lot bigger than 1.8 times 10 to the minus 3. So we can absolutely ignore that little minus X. That means X squared equals Kb times Cb, the concentration of the base, or X equals square root Kb times Cb. So the hydroxide, which is what X is, square root Kb times Cb, square root 1.8 times 10 to the minus 5 times 0.25, that comes out to be 0.0021 moles per liter. From there, you can find POH minus log of 0.0021 is 2.67, and then pH would be 14 minus 2.67, 11.33. This is the pH of the ammonia solution without the ammonium, and you can check yourself. The pH is larger than 7. It's basic. That's good. Ammonia is a base. Now, again, from last time, I'm going to advertise. If you want to do one-stop shopping, you can also find the pH using the weak base expression, 14 plus log square root Kb times Cb. And you don't have to go through all these different results. And as long as 100 times K is less than C, which it is, you're totally good to go. So this is how to find, again, as a reminder, the pH of the weak base. In this problem, we still have the 0.25 molar ammonia, but now we have 0.10 molar ammonium chloride, all right? And we talked about how the ammonium is a weak acid. We talked about how the chloride doesn't affect pH, so we're going to ignore it. And we also talked about how adding an acid to a solution should make the pH go down, become more acidic. So that previous 11.33 number, the final answer should be a pH number less than that. So anyway, if you want to do a problem like that, set it up again in an ice table. We expect that the pH is going to go down, but we should actually, of course, make sure that that's the case. So let's check it out. So ice table, once again, only now we have some ammonium to begin with. Now, 0.25 molar ammonia and 0.10 molar ammonium, and we don't have any hydroxide. Now, in an equilibrium, you must have some of everything, and that includes hydroxide. You can't have minus X if it's at 0, for example. So we must have plus X for both ammonium and hydroxide. Equilibrium means you have all species present in some form. So ammonia is still going to be minus X. ammonium and hydroxide will still be plus X. But now at equilibrium, you can see 0.25 minus X. For ammonia, ammonium 0.1 plus X, and X would be just the value of hydroxide. We can set this all again equal to the Kb for ammonia, because this is the Kb expression for ammonia, 1.8 times 10 to the minus 5. You can see we have X for hydroxide still, but for ammonium now we have 0.10 minus X, and for ammonia we have 0.25 minus X. Now this expression is also a quadratic formula, and if you want to get out your solve function and solve for it, that's fantastic. You can absolutely do it. However, remember that 100 times K is certainly less than either of the C's. It's supposed to be the Cb, the concentration of the base, which is 0.25, and we saw that counted. However, in this case, we're even more justified in saying that, boy, that little X there isn't going to mean anything, because X was hydroxide, and we predicted that by adding ammonium, a weak acid, it's going to move the reaction by Le Chatelier's principle to the reactant side, to the ammonia side, and in the process it's going to take hydroxide, and hydroxide is the X. So X was already small. It was 0.0021, and that's much smaller than 0.10 and 0.25. And now in this problem we predict X is going to be even smaller. So this is going to sound maybe a little bit cheesy. However, you can actually ignore both the plus X and the minus X in these problems, because if you take 0.10 and add a number smaller than 0.0021, it's still going to be 0.1. And the same thing, 0.25 minus a number smaller than 0.0021, it's still going to be 0.25. Significant figures here are actually your friend. They're making your math life easier. And I know in Chem 221 you thought, boy, this is never going to happen, but really it is possible, because you have to cut these numbers off at the hundredths spot, XX, the second decimal to the right, number to the right of the decimal. It doesn't make any difference. So you are absolutely justified in canceling both the plus X and the minus X. Well, if you do that, then you get X, the hydroxide, equals Kb, which is the 1.8 times 10 to the minus 5, times the concentration of ammonia divided by the concentration of the ammonium. So 0.25 divided by 0.1 times Kb, that's how we're going to solve for the hydroxide. And hydroxide here then, the X comes out to be 4.5 times 10 to the minus 5. And let's have a quick reality check. Earlier I said that 0.10 plus the X was going to be 0.10 by sig figs. Lo and behold, 0.10 plus that really small number is still 0.10. Cutting it off at the hundredths, it stays 0.10. And the same thing for 0.25 minus X. It's still 0.25. So there was no reason to add in the plus X or the minus X in this problem. X is 4.5 times 10 to the minus 5 moles per liter. And from there, we can turn this into POH minus log of hydroxide, 4.35. pH is 14 minus POH, so 14 minus 4.35, 9.65. And if you remember the number from before, which was 11.33, our pH has definitely become more acidic. So having a pH go from 11.33 to 9.65, that's a move to the acid side of things. It's still basic, all right, because you still have ammonia, but it is definitely a move towards the acid side. So we can use here to justify this, the common ion effect. We added ammonium, the reaction shifted to the left, hydroxide went down, hydronium went up, and pH went down, which is what we saw. Or you can just remember that, hey, you're adding an acid and that pH should become more acidic, and it certainly has. So common ions here are really interesting. You do have both ammonia and ammonium present in solution at the same time, and there's no way that this would work for strong acids and strong bases. This only works for weak acids with conjugate bases or weak bases with conjugate acids. It's a really interesting phenomena. Weak acids and bases have a lot more to offer than you might have thought about at first glance.